here. So now we can see, I will show you how the generalized silo canceller gives also similar solution using this decomposition into two components. So it will give us a solution to the LCMV, which is a generalization of the MVDR. Because instead of one constraint, we have multiple constraints. So what do? We can write the filter as two components, what I called here H0. So we will call it minimum norm. We will see. It doesn't really matter how do you call it. But instead of finding this filter, we find two filters. One is H0 or HMN, minimum norm, and we find another filter here. So the objective is to find a filter here without needing to add the constraints. So we separate this structure into two things like this. One, the top, is just to find a solution that satisfies the constraint. And at the bottom, we find the solution of the filter that satisfies the minimization of the power or the variance at the output. This is the idea. Okay. So the minimum solution, so we just need to satisfy the constraint. So for the LCMV, what is the constraint? The constraint looks like C, the matrix of constraint, H, minimum norm, or H0 that we called it here. It doesn't really matter. We want it to be IC. This is the vector of the values of the constraint. Just like we saw, this is the constraint of the LCMV. So the solution for this is this. This is the minimum solution, minimum norm solution. Okay? And so we have a solution to this one. Now, the blocking matrix, we can obtain it such that we will have, if we have C constraints or MC constraints, if we have MC constraints, so the number of channels here will be M minus MC. Okay? So we need to find the blocking matrix. Okay? So the blocking matrix is actually the matrix that spans the null subspace of C. So we need to get it from here. How do we find? You see, in this case, in the MVDR, it was what we wrote before, okay? So it's a blocking matrix. We showed an example how to block the desired signal. So actually, if we know the steering vectors, we can find, we know the steering vectors of the constraints. So we know the matrix C. So we can find a blocking matrix of size M by M minus MC such that this will be satisfied. So actually, we say that the blocking matrix spans the null subspace of C. This is the way to tell it, okay? Because this is satisfied. Now, so we can find a solution for that, okay? What is the solution? The blocking matrix. Okay, it looks like that, just like we showed before. So the blocking matrix can be written as a matrix P, PC, and this matrix is identity matrix of size M minus C by M minus C. This is the identity matrix. The rest are 0. And this is a matrix that projects the input. So it's a projection input. This is a projection matrix that projects the input signals here, project it onto the null subspace of the constraints. Okay? So of course you can see what is the solution, but this is known. What are the projection on a space? If you're not familiar with subspaces, signal subspace, null subspace, and projection onto a subspace, I can give you a very good reference to read. So there is a book which is called Mathematical Methods in Signal Processing. Okay, so it's a very basic book, more than about 20 years ago, maybe slightly more, which will give you all the basic mathematics of signal processing. So if you're not familiar with this null subspace and projection onto subspace and so on, it's important to read this stuff if you're working with signal processing and array signal processing, image processing, EEG, and other types of signal processing, also machine learning. You will need that. Okay? So this is a way to write it. Okay, so we can find, you see, so if we know the constraint matrix, if we know C, we know B, just like with MVDR. With MVDR, if we know the steering vector, we can find, we know what is the blocking matrix. This is the only information that we know. So if we know the steering vectors here in the constraints, we know how to project to the null subspace. So the rank of this null subspace of C is M minus the number of constraints. So this is the rank of the subspace. So we can immediately, we can get very easily the blocking matrix. By the way, it's not the only solution. There are other solutions. And there are some works about finding a better way. Because which solution out of the, that when it's just like basis functions. See, when you span a space, you can span it using different types of basis functions. For example, just like time domain, frequency domain, time frequency domain, so on. So you can find basis functions that span your space of signals. So also, you can find different blocking matrix that span the null subspace of the matrix C. So this is just one solution, but it's not the only solution. So there are some works that compare different solutions and try to find for different applications how to choose this blocking matrix. But just here, I want to give you just one of the solutions. So we found B. We found H minimum norm. We found this. We found the blocking matrix. Now we only need to find W such that we minimize the variance at the output without any constraint, because we already satisfied the constraint here. So we don't need to find W with additional constraints. So it's unconstrained minimization, which is much simpler. It's just like adaptive filtering. So we can either do offline, but there is no advantage of doing offline, because if we do offline, we can find a solution of the LCMV. But we can do it online with adaptive filtering. So it gives us the flexibility of implementing LCMV with adaptive filtering. Okay? So we minimize here, and we get, this is the offline solution, but we can find solution using adaptive filtering. Okay, and then we have, this is just the mathematics to show different derivations, to show the equivalence. This is the implementation with STFT. I talked about it yesterday, so we can skip. And this is the reference number 17, which is only like 4 pages, which It's very nice to read. So I recommend you to read this paper about the equivalence between LCMV and GST. So you see, try to read papers which are interesting. It will give you inspiration in your research. Okay? Okay, now we move on to fixed beamforming. Before we move on, I will show you a short clip. Actually, I have two nice short clips. Okay, I'll show you. Okay, I have a few interesting clips. Okay, first I want to show you what is signal processing, so you know, but you'll see maybe some applications which are very important and you don't know. And then I'll show you maybe also benefits of spoken language technology. Show you two.
What is signal processing? Signal processing is a branch of electrical engineering which pulls meaning from the broad sources of data that are all around us. But what does that mean exactly? It means signal processing is at the heart of our modern world. Signal processing powers modern communications.
How can I help you?
Modern entertainment, and tomorrow's transportation. Signal processing is at the intersection of biotechnology.
Voice print access.
Access granted.
It's in our social interactions. Learning to anticipate our needs and emotions. Helping us hear the world around us and to better understand it.
Salam, chetari khubi? Hi, how are you doing?
To bring new life and help us heal. Signal processing brings the world to our homes, adds clarity, and puts it in our pockets. Signal processing documents our cherished memories, helps to keep us safe, and powers the world of finance. Signal processing, processing the future.
Okay, so you can use it when somebody asks you, what do you do? So you can talk about, and I'll show you another nice video about using speech with deep learning and machine learning. This is also a nice clip.
Don't you see it was Orville who buried the crowbar in the crypt, not the Leon burger? Don't you see it was Orville who buried the crowbar in the crypt, not the Leon burger?
What's a Leon burger?
It's a big dog.
Did you guys leave a window open when you recorded this?
You got a problem with that? I'm doing a murder mystery, only there's too much wind noise, so we have to redo a key line. But this isn't about Leon burgers or murder mysteries. It's about signals and computers that learn. But you knew that from the title.
Just for fun, read it completely flat.
Don't you see? It was Orville who buried the crowbar in the crypt, not the Leon burger. Brian King was an intern when he helped develop this automatic dialogue replacement program that fixes the wind problem and my purposely crummy read beautifully. Brian's software will make my voice match the original read exactly. Normally this would take you an hour to match, and it still wouldn't be very good.
I heard that.
Car scene, take one.
And action.
Don't you see? It was Orville who buried the crowbar in the crypt, not the Leon burger. Very impressive. So what role does signal processing and machine learning play in this program?
So it's really a two-step process with that.
Just I want to mention that something like that with classical signal processing was a big, big problem. But with machine learning and combining signal processing and machine learning, now it's possible to do things which were thought as almost impossible. And I have many examples like that in many areas. So that's why I encourage you to learn signal processing and deep learning, machine learning methods, and then combine them. Because I think in our area, this is the future of working applications and theory, combining application and theory, and mathematics and the physics part to understand the models, and also to use machine learning to combine to get solutions. Actually, it's related to what we did, adaptive. So with machine learning, you adapt the parameters of the models to achieve a certain results. So it's quite amazing, see, what they showed now.
Signal processing part, we're taking these audio signals, so your speech, and analyzing it in such a way that we can figure out the important parts of the signal. And then the machine learning part is aligning those features kind of every step in time. The coolest thing is being able to do things that have previously been impossible to do and no one's been able to do before. It's a little bit like magic.
Brian told me about another application of signal processing and machine learning where instead of using sound waves, they're using brain waves. Xin Zhang is trying to tell the computer to move this arm brace using his thoughts. What are you thinking about to make the arm move?
Just grasping my hand.
Grasping your hand,
Yeah.
and that allows it to bend.
Yeah. Yes.
He doesn't have to grasp his hand, he just thinks about doing it. There! That's not him moving his arm. That's the arm brace receiving his brain signal from the computer. Xin Yi Yang heads up this brain-computer interface project. Why do you choose to use the action of grasping to move the arm?
Studies have shown that if you imagine a hand movement, it will create some very distinct changes in the EEG signals.
And how does signal processing play into this whole thing?
First, we can use signal processing methods to analyze the signals to look for specific patterns that occur when you perform a movement. Another very important application is to remove noise from the brain signals. The third one is to extract important information from the brain signals. The machine learning will try to distinguish different brain patterns. It will be able to distinguish whether the person is imagining a movement or he is resting. We can use this technology to help people with limited mobility to operate certain devices, for example, a prosthetic hand or a wheelchair or a computer. If you can't use the keyboard, you can use this technology by using your brain signals.
There's another recent development that couldn't exist without signal processing and machine learning.
What do you do for fun?
¿Qué haces para divertirte?
Li Deng and the team at Microsoft came up with this translator. With this, he spoke with me in his native Mandarin. What's been the biggest challenge in creating the Skype translator?
最大的挑战是实现高精度的语音识别和机器翻译。
The biggest challenge is to achieve high-precision speech recognition and machine translation.
语音识别是一个核心的信号处理的问题。
Speech recognition is a key signal processing problem.
将机器学习应用到语音识别，精确度大大提高。
Machine learning has been applied to speech recognition. Accuracy is greatly improved.
Where in the world do you wish to travel?
By the way, there are some devices now that on a wearable device like glasses, people who don't hear anything. So they can listen to somebody, and they get the translation of what the person says, and it's possible in any language, even if they don't understand the language, and it's put on the inside, on the screen, on the glasses from inside, so they can read what he says. Think about, now there are unlimited applications that people are working on, companies, and you can be part of that. So amazing, amazing devices, okay?
¿Dónde en el mundo te gustaría viajar?
A Rusia.
To Russia.
¿Y tú?
And you?
Everywhere.
In this translator and our other two examples, signal processing algorithms processes and extracts information from data, while machine learning algorithms recognize patterns and make recommendations. Signal processing is prevalent in thousands of humanities tools, like cellular communications, financial markets, aviation, radar, medical imaging, robotics, and digital videos. Machine learning is prevalent in a large number of prediction problems, like weather forecasting, games, search engines, traffic patterns, social networks, and recommending movies you'd like to watch or books you'd like to read. Everything in the universe can be described as a signal in the form of a wave. Vibrating stars, vibrating quarks, even vibrating Leon burgers.
Okay, now we move on to fixed beamforming. So I will show you that now after you learned also the main things in array signal processing, now the rest, or what I'm going to show, I'm going to talk about fixed beamforming and adaptive beamforming. But instead of doing all over from the beginning of what is fixed beamforming and so on, it's just like the mathematician. I need to show you the differences between fixed beamforming and what we learned about signal enhancement, multi-channel signal enhancement. Once you know the differences, what we did before is applicable to fixed beamforming. It's applicable to adaptive beamforming, okay? So everything, now the rest of the talks, the other topics, fixed beamforming and adaptive beamforming, are just derivatives or of some of what we already talked about in length. So it will be much shorter. I'll just talk about the differences. Okay, but this is what is important, because you are familiar with the mathematics of signal enhancement. So I'll show you the differences, and then the mathematics is very similar. That's why it's important to study related areas and problems, because you can apply one to each other, and you can learn from one to each other. Okay, so the signal enhancement problem, let's talk in the frequency domain, because now after we talked about time domain, we'll do fixed beamforming and adaptive beamforming in the frequency domain. If you like to do it in the time domain, you will also know, because you're familiar with the methods. Okay, so for simplicity, we work in the frequency domain. So we have M channels. So we have a vector of measurement for each frequency, and we assume that we can write it as x1f multiplied with a steering vector, because it's a directional source, plus noise. I will put here be like this. This is the vector of noise for the frequency f in all the M sensors, okay? And then we try to find an estimate of the desired signal in the reference channel, in the reference sensor by obtaining a linear filter that looks like this. And we found various methods. We defined performance measures and obtained optimal filters according to these performance measures. So this is signal enhancement. Okay, multi-channel signal enhancement. Now, which information did we use? Okay, so we used information about the relative transfer function. This is the information that we use. Relative transfer function, which is an important part. It contains important information. It means that if we have a source and the array is somewhere, so we know what are the reflections from the propagating wave, how it reaches, how it is measured in the array. So this relative transfer function. What do we additional? What do we know? Okay, what do we know in addition when we find these optimal filters? So we assume we know also Rx. Oh, no, we call it in the time domain it's R. So the correlation matrix in the frequency domain, we call it phi. Phi x. So this matrix, m by m, which means that we know the correlation between desired components from two sensors, any two sensors for the frequency f, every frequency. But we know this correlation. In addition, how do we know this correlation? Actually, I don't need all this matrix, because I know if I know D, it's enough that I know the variance of x1. Okay? Let me write it, okay? So this correlation matrix is the expectation of x so it's actually phi x1, the variance of x1, multiplied with the dh. So if I know D, and I know the variance of the desired signal in the reference channel, I know this matrix. In addition, I assume that I know phi v f. Okay, so you can write it like this. So I know also this matrix. So I know the correlation of the noise components in every two sensors, the correlation between any pair of two sensors, which is also, it means that I know what is the environment, the background noise in the environment. I know, using the sensor array, I know how they received or how they correlate between two sensors. So this enabled me to obtain an estimate of the desired signal in the reference sensor. Now, for fixed beamforming, I don't have all that information. I don't know the environment. because I design it with a device or sensor array without knowing the environment. Afterwards, I put it in a different environment, but I don't know anything about the environment. What I do know. Okay. So here, I know that the relative transfer function. Here, I don't try to estimate the desired signal because I don't know what is the desired signal. So what I try, the model is different. So the model is that I have a signal from a certain direction. So I have a signal from a certain direction. Let's call it even, okay, we will call it x1f. From a certain direction, but here I don't use the relative transfer function because the relative transfer function requires to know the environment, the source, how the propagating waves, heat, surfaces, reflections, room, reverberation of the room, and so on. All that included here. So I don't use this. I use a simple far-field propagation steering vector without any reflection. So I will call it f cosine theta. Okay? So it only in three-dimensional, okay, it depends on theta and phi, okay, the direction. So I only know the direction of the desired source. That's it. I need to know the direction of the desired source. Plus noise. I don't know the noise. I don't know what type of noise I will have. So, okay, so what can I do? What can I assume? How to proceed with this problem? So first, what I will try to do, that if I will try to estimate ZF, I will try to apply a filter to Y. But I don't know what is the statistics of the desired signal. But I know the direction, and I don't know the reflections. So I don't take the reflections into account. So what I require, that if I apply the filter that I find to the direction, to signal that comes from that direction. So this is the steering vector, far field steering vector without any reflections in the environment. So I know that. I know how to find this steering vector. We talked about it when we talked about overview, but I will show you. It's enough that I know the position of the array, the configuration of the array. Once I know the configuration of the array, I can find this steering vector. But it's different than this one. This contains a lot of more information of the environment. Here I don't know the environment. I just assume that the desired source comes from a certain direction. Theta 0, let's call it theta 0, okay? Theta D, theta desired. From a certain direction, theta D. Now, in order that a signal that comes from this direction will not be distorted, I will require that this is 1. It's constant for all frequencies. So it's a distortionless constraint for a certain direction. But if I put this array in a certain environment, okay, with reflections, reverberation, and so on, it will not estimate x1. It will just not distort the direct path. But the reflections, of course, they will be distorted. So here, using a fixed beamformer, we will not estimate x1. We will get a source from that direction. So in case the environment is without any reflection, this is an estimate of x1. But if in a real environment with the reverberations and so on, it's not an estimate of x1. So you need to understand that. But because we don't know the environment, we don't know the relative transfer function, we just know or design the beamformer towards a certain direction, theta d, this is what we apply. So this is the distortionless constraint, which is different than what we used here. In addition, I don't know what is the noise environment because I designed it in advance without knowing the environment. So what I can do, I can try to design it relative to certain environments. The simplest environment that I can design it to is either when I have white spatial noise or when I have diffuse noise. These are the simplest environments. Because what does it mean, white spatial noise? Like thermal noise. So we always have some thermal noise. And diffuse noise, it means that the noise comes from all directions, or it means that I don't know where the noise comes from. Because in the real environment, maybe it comes from this direction, I don't know. So I assume it may come from any direction. But of course, you can assume a different noise field. For example, you can assume that the noise comes from all directions like a cylinder, from horizontal directions. But you don't know which direction, so you assume that it can come from any direction in the horizontal plane, but not from any direction, three-dimensional sphere. It's also okay. But you assume something. So regarding this noise, I assume phi v is known for certain environments. For certain environment. Usually, we assume either white noise, white spatial noise, white noise field, like thermal noise, okay? Or diffuse noise, or you assume other things, okay? But for here, just for simplicity, we will assume either this or combination of this. So we can continue from here. Once we understand these differences, now we can take the solutions that we did here to here. But the performance measures, can we define mean squared error? Actually, we cannot define mean squared error because it's irrelevant. Because we don't know the signal. We don't know the signal. We don't know the variance of x1. We try to do it. So we need to define performance measures and find optimal fixed beamformers based on this information. Okay? This is the most important thing, to understand what is the problem, what we know, and how to proceed. Any questions? Okay. So now, everything will be much simpler. We will define the signal model and problem formulation. We will talk about linear array model, performance measures, spatial aliasing, and fixed beamformers, which are optimal based on the definitions of the performance measures. So this part will be quite straightforward. Okay, we will talk about it because we understand what are the differences and we know the solutions that we did with signal enhancement. Okay, so this is the model like we did before. So first we define the steering vector for a certain direction. This is the steering vector for a certain direction. For this kind of array, uniform linear array, just like we did before. So we assume uniform linear array with inter-element spacing equals to delta. and the signal comes from a certain angle, theta. And then, because we don't have any reflections in the environment, so this is the steering vector that, assuming that we have a free field, no reflections, only delays. You see, only delays. So for fixed beamformer, because we don't design it to a specific environment, we assume only that it's like far field direction. Okay? Important to understand the differences. So we call it df cosinus theta, because it depends only on the direction. Now our model is like this, that y equals to d multiplied with x. Actually, it's the same as x1, you see, because the steering vector here, it's always the reference channel. If the first one is the reference channel, we will always have here 1. The others are just delay in time, which in the frequency domain is exponential, that looks like that. So this is our model. And we don't try to estimate x. No. This we tried with the signal enhancement. We don't know how to estimate a signal. We just want that the beamformer will not distort the direct path from a certain direction. But we want to suppress noise as much as possible. Okay? So even here, we assume that when we apply the beamformer, now instead of filter, with signal enhancement, we call it filter. Here, we call it beamformer. It's just a name, because here we talk about beamforming, but when people say beamforming or beamformer instead of filter, it means something. Filter, it means that we know information about the statistics of the signals, and the desired and the noise. Beamformer, it means that we don't make assumptions about the environment. If we make assumptions about the environment, we'll see. We will talk about adaptive beamformer. We will move on. But first, I want you to understand. Beamforming, it means that we know the direction. We don't know the relative transfer function. And we don't know the signal, the statistic of the signal. We just want to keep this direction without any distortion, the direct path, without any distortion. Okay. So this is the model. Let's continue, just like we did. Let's compute the correlation matrix of y. So the correlation matrix of y is variance of x, which we don't know, d transpose conjugate, okay? D we know, because we know we will design the beamformer that this direction, any signal that comes from this direction will not be distorted. Plus this correlation matrix of the noise, which we don't know. That's why we will optimize the beamformer with respect to white noise, maybe with respect to diffuse noise, maybe with respect to combination, and so on. Okay? Because we need to assume what is the noise environment. We don't know. Now, linear array model for beamformer, so it's just like that, similar to what we did with the signal enhancement. So we have two components of the X filter desired plus residual noise. Okay? But we don't make any assumptions about the desired signal other than it comes from a certain direction. So if we write the filter desired, when we apply it like this. And the residual noise will be the beamformer that is applied to the noise signal. now we can compute the variance of the output of the beamformer. So it's composed of two components. One is the variance of the filter desired, and one is the variance of the residual noise, like this. Okay, so when we, this is the constraint of the distortionless constraint to a certain direction, you see? And we will define performance measures that will optimize the filters, the beamformers, under certain conditions. Okay? So performance measures. We will define performance measures. The performance measures will be different than the multi-channel signal enhancement. Because here, performance measures are for a certain given environment and for given signals. Because we know, you see, we don't just know the relative transfer function, which we need to know the environment, but we also know the variance of the desired signal in the reference channel. And we know the correlation matrix. Here we don't know. So we need to define maybe other performance measures. For example, MSE, we cannot define. We cannot define distortion index because it depends on the signal. We don't know the signal, or things like that, okay? So we will see which performance measures we are able to define now for this problem, and how to optimize, how to find optimal beamformers based on these performance measures. Okay? So the most important thing in this till now was to identify, to understand what is a beamformer, what is a fixed beamformer, and what is signal enhancement. It's based on what you know. What are your assumptions? And then we will talk also, maybe you will ask, after you understand the differences and solutions and what do we do with it, you can think, okay, now I have a real problem in practice. I go to my work, go home, I think of a certain problem. Is it better to use a filter that we learned using signal enhancement or a fixed beamformer? After we learn, I will ask you this question, so you have time to think, okay? And then you can give me some answers. When to use each one of them? When one is better than the other, okay? So we will have a break now, and then we will talk about the differences and optimal beamforming method for fixed beamforming.